Welcome back to today's Explainer. We're diving right into a classic, and honestly, pretty clever coding problem. We're going to figure out how to find the rightmost nodes of a binary tree. So whether you're actively brushing up for technical interviews or you just, really enjoy a good data structure puzzle, this is an absolutely fantastic exercise for us to break down together.
Okay, first things first, let's pin down our exact goal. We need to traverse a given tree and return an array that contains only the values of the rightmost nodes at every single level. So, working our way from top to bottom, the target output array we're looking for right here is going to be 1, 3, 6, and 11.
Now, at first glance, your intuition is probably screaming a super simple solution at you. You might be thinking, well, why not just traverse down the right side? It seems so obvious, right? Like, just start at the root, follow the rightmost branch all the way down to a leaf node, and collect those values as you go. Boom, done.
But, well, let's actually test that naive approach for a second. If we trace a path straight down that rightmost branch, we grab nodes 1, 3, and 6. But wait, check out the bottom left. Because this specific tree actually happens to be left-heavy at the very bottom, traversing only the right branch completely misses node 11. It's totally left out, and our output falls short. So the absolutely crucial takeaway here is that a single branch traversal, it's just never going to be reliable. Our true solution requires us to process the entire tree systematically. We can't just dive deep down one single path. Actually, we need to sweep across the tree horizontally. That's the only way to guarantee we don't miss any of those deeply nested nodes hanging out on the left side that might, surprisingly, represent the furthest right point of their specific level. And that brings us to a much more robust approach, level order traversal. Now, this is a classic breadth first search, or BFS, technique. But here's the catch. A standard BFS doesn't really give us explicit markers for when one level ends and another one begins. It just sort of visits nodes continuously. So, we're going to need a specific twist on BFS to process things strictly one level at a time. The fundamental concept to keep in mind here is that the children of the current level's nodes make up the entirety of the next level.
To actually execute this, we can break the core logic down into two incredibly simple steps right inside our main loop. Step 1, determine the level size. By checking the exact size of our queue right before we start popping nodes, we know exactly how many nodes exist on that current level. And then step 2, process that current level. We just pop those nodes out one by one and immediately push their children into the queue for the next round.
All right, let's walk through this in action. We kick things off by initializing our queue with the root node, which is 1. Now, at this exact moment, our queue perfectly represents the first level of our tree, and, as you'd expect, its size is exactly 1.
So now we process level 1. We pop that root node right out. Our queue size temporarily drops down to 0, but almost instantly upon popping node 1, we push its left and right children, that's nodes 2 and 3, straight into the queue.
Now, take a look at the current state of our queue. Because we removed the only level 1 node and swapped in its children, the queue now perfectly represents level 2. Checking its size tells us there are exactly 2 nodes to process. I literally cannot stress this enough. This size snapshot is the absolute secret sauce to the entire algorithm.
Let's keep this momentum going. We know we need to process 2 nodes for level 2. We start by popping node 2. And as we do that, we grab its left and right children, nodes 4 and 5, and push them right into the back of the queue.
To finish up processing level 2, we pop the second of those 2 nodes, which is node 3. Now, node 3 only has a left child, node 6, so we just push node 6 directly into the back of the queue. Easy enough.
Okay, let's just pause for a second and check on the queue state again. We completely finished processing the 2 nodes from level 2. So the queue now holds nodes 4, 5, and 6. And if we check the queue size, it's exactly 3. This totally confirms that our queue is perfectly tracking the 3rd level. It's working like a charm.
So, if we fast forward to the end of this whole process, how do we actually capture our target output? Well, it's remarkably simple. Because we know exactly how many nodes are in any given level, we just use a loop for that specific count. When we hit the very last iteration of that loop, which means we're looking at the last node processed for that level, we simply record its value. Doing this level by level gives us our perfect output array, 1, 3, 6, and 11. Let's see how this actually builds out in Python. We start by setting up our queue using a dequeue, and that's perfect here because it lets us pop from the left super efficiently, in O of 1 time. Once we're inside our main while loop, we grab that level size right off the bat. That integer completely dictates our inner for loop, ensuring we only pop the nodes that belong to the current level. Inside that inner loop, we append the children for the next level. And here is the crucial part. If I equals level size minus 1, we know for a fact we've reached the end of the current level. That's our explicit cue to append that specific node's value to our final results array.
All right, let's bring it home with the complexity analysis. The time complexity is big O of n. Why? Well, because our level order traversal visits and processes every single node in the tree exactly one time. For space complexity, it is also big O of n. Our queue has to store the nodes of the next level as we're actively processing the current one. In the absolute worst-case scenario, like say the final level of a perfectly balanced tree, the queue is going to hold roughly n over 2 nodes. And in big O terms, that just simplifies down to O of n space.
And there you have it. Understanding how to just take a snapshot of a queue size right before processing gives you absolute total control over tree levels. It's a real game changer. So what other hidden patterns do you think level order traversal could reveal in more complex data structures? Keep that thought bouncing around in your head as you apply this powerful queue-based BFS pattern to your next coding puzzle. Thanks so much for learning with me today, and I'll see you in the next explainer.